This week we're going to be talking about resonance and resonance in several different types of resonance. We're going to talk about closed tubes, open tubes, strings, all different kinds of ways of getting resonance. And we'll even go off topic, but a little bit from sound onto electronics, kind of demonstrate what resonance looks like. Symbols and units we're into, some are repeats, right? Frequency, we have lambda, we have wave velocity. We're introducing resonance length, which is just a length in meters. And now we have to start thinking about temperature. There's temperature in Celsius, which is what our equations are going to be in because we're using SI units, but there's also temperature in Fahrenheit. And so we're going to have the formula for converting from Fahrenheit to Celsius, which I'm sure all of you remember. We're also going to introduce force. The tension in a string is the force we're going to be looking at. So F sub T, the units of force are newtons. And we're going to be introducing the mass per unit length for strings and wires. Mass per unit length is just the mass of a wire divided by its length. Resonance occurs when a narrow range of frequencies manage to efficiently energize a system. And so, you can pluck a string, but when you pluck a string, it's not going to give you just any note. Why? Well, you put energy into it, but there's only a narrow range on which that energy efficiently excites the string when it's vibrating. Your musical instruments are just one example of resonance. You can blow in the bottle on a bottle, make it create a note. That's the same thing we're doing with musical instruments. Electric circuits also have resonances. That's what we use to make low pass, high pass, and band pass filters. If you want to see a really cool instance of resonance in real life, watch the little YouTube video of the Tacoma Narrows Bridge. Basically, wind started coming down through the valley at a consistent velocity, and just like you're pushing a child on a swing, the wind kept pushing the bridge and got it moving pretty bad. Um, Watch it, the bridge. It's just unbelievable to see concrete doing what it's doing in that video. Now, resonances occur in structures, large structures in particular, all the time. We've since the Tacoma Narrows Bridge, we've since learned to decide where they're going to be and build it so that they're in places where they're unlikely to be excited. And in fact, at the top of very tall buildings, they'll sometimes have a very large mass that's there just to help them dampen the resonance of the building in the wind. Because the top of a building can move quite a bit. Top of a 110 floor building can move quite a bit in the wind if you're not doing something about it. And also, when you think about resonance, think about when you're swinging, you have to hit it, you have to kick your legs at the right moment. If you kick your legs at the wrong moment, you actually dampen the motion instead of increasing the motion. Show you a quick example of a LC or RLC circuit. Um, this is just a inductor, which is inductors are very often just coils of wire around some ferromagnetic material. This is a capacitor and a resistor. We'll learn more about all of this later in the semester. But when you look at this circuit, it has a particular resonant behavior. So I've stuck in some values for these that are fairly realistic that gives us a resonance around 500 hertz. And you can see this resonance response um, at where it, it very efficiently passes energy around the resonance, but that tails off on either side. Another thing you'll notice in this graph is I have a log scale in terms of frequency. And very often when you start talking about frequencies, we'll use a log scale. And that's simply because the log scale is very natural for using in frequency based on how we perceive sound, which we'll get to later in the semester. When we talk about resonance in a vibrating string is fixed at both ends. And so it can't move on the ends. And so if you're imagining, I'm going to imagine cutting this off. So this portion is right? That's the portion of the string that's vibrating. Well, it's fixed here and it's fixed there, right? We could also go with it's fixed here, it's fixed right there, and it's fixed right there. You can make a string vibrate that way. And this is the fundamental, or the first harmonic of a vibrating string. The first overtone stretches it to there, second overtone, third overtone, etc. This keeps going in half wavelengths. Why? Because every half wavelength you have the opportunity for another node, right? And I'll show you where those nodes come from on the next slide. A vibrating string is really two waves traveling in opposite directions, and that creates a standing wave. How does it do that? Well, if you remember our equation for a wave moving to the right plus a wave moving to the left, when we pull out some trig identities, sine A plus B and sine A minus B, and we put them together, because this is sine A minus B, this is sine A plus B, we get these two terms add, and we get 2 sine A, 2 cosine B. These two terms, when you add them together, what happens? That term goes away. So we're left with 2a sine of 2 pi ft cosine of 2 pi over lambda times x. All right, so now the shape of it in space, right, is defined by this cosine term. So the shape of it in space means it has to look like a cosine. And what's it doing in time? Well, in time, it's vibrating back and forth between these two positions. And then you have these nodes where it's not moving at all. Right? So in time, it's going back and forth, back and forth. It's staying fixed at the nodes. This is just these two waves traveling back and forth through each other. They're always adding to zero right here. They're always adding to zero right there. And they're always adding to zero right there. And this, of course, would be the first overtone, the fundamental being just this. So we have a feel for what wavelengths, right? We have a feel for what wavelengths are going to resonate in the string. And we can solve our equation that we had up here. Our equation L is N times lambda over 2. And N, of course, is either 1, 2, 3, etc. We can solve that for lambda. And lambda is 2L over N, and N is 1, 2, 3, etc. Right? N is first harmonic, second harmonic, third harmonic. Now, this is a wave traveling in a string, and the velocity of a wave in a string is not the same as the velocity of a wave in air. The formula for velocity of a wave in a string is simply the square root of the tension in the string divided by its mass per unit length. Right? Square root of the tension in the string divided by the mass per unit length. That's the wave velocity in the string. And so now we can use that wave velocity and this wavelength to figure out our frequency from our good old equation, V sub W equals lambda F. So now we know what frequencies will resonate once we figure out the wave velocity in the string. Other types of resonance. You can have a pipe that's open on both ends and get it to resonate. And if you look at it, what's going on? Here, the pressure has to be atmospheric. On the other end, the pressure has to be atmospheric. In the middle, it can change. And if you think about this as a node and that as a node in terms of pressure, then you can quickly kind of see where, oh, this is going to be just like a string. The pressure can be maximum in the middle, back to atmosphere on each end. And so the pressure in the middle is going up and down, up and down, up and down, up and down. Right? And so again, we get to lambda is 2L over N, where N is your first harmonic, second harmonic, third harmonic, etc. In this case, the wave velocity is the speed of sound because the medium in which the wave is traveling is air. If we think about a tube that is closed on one end, oh, and trivially, you can get the same result out of a tube that's closed on both ends. It just doesn't make a very good instrument. So if you have a pipe that's closed on just one end where it's capped and it's an atmospheric pressure on the other end, then here you get a different situation, all right? We can have a quarter of a wavelength, and the next up is not a half of a wavelength. The next up is 3/4 of a wavelength. And then after that, you have to add in, every time you do this, you have to add in a whole half wavelength. All right, so you add in a whole half wavelength to get to, now we're at 3/4 of a wavelength. And you add another whole half wavelength, and now, oh, sorry, 4, right? And so this is 5/4. This is 7/4. And if you solve for lambda, lambda is 4L, lambda is 4/3 L, right? And so the length here more generally looks like this. And if we were to solve this for lambda, lambda is going to be L over 4, right? So quarter of a wavelength, 2n minus 1, where again, n is first harmonic, second harmonic, and third harmonic. All right, so lambda has to go in quarter of a wavelengths, but we skip the even ones, which is all this 2n minus 1 does. We're skipping the even ones. So 1/4, 3/4, 5/4, and I did that wrong. 4L over. There we go. So lambda is 4L, and then lambda is 4/3 L, all right? And lambda is 4/5 L, 4/7, 4/9, etc. Finally, we have to talk about the velocity of sound in air, because it is not a constant, and it depends on more than just temperature. We're going to just go with it depends on temperature. And the velocity of sound in air is approximately 331 meters per second plus 0.6 meters per second degrees C times the temperature in Celsius. And to convert from Fahrenheit to Celsius, Fahrenheit, temperature in Fahrenheit, minus 32 degrees Fahrenheit, times 5/9, and it's really 5 degrees C per 9 degrees Fahrenheit, right, times 5/9, gets us to our temperature in Celsius. That's it for this week's preview. Good luck in getting into the problems and into the discussions. I look forward to talking to you.